I have you loud and clear.
Hello.
Welcome. Science.
And that is to say,
Physics,
Medicine.
nature,
or
Space.
Time.
The brain. Life.
The universe.
Hello. This week, the looming crisis posed by plastic. It doesn't break down naturally, and most of it ends up either in landfill or it washes into the sea, where it's now causing a marine catastrophe. But science is fighting back, and this week we're hearing from the technologists who are making an environmentally friendly form of plastic from poo, and talking to the man who's turning waste plastic into road repairs.
Plus, in the news, could we finally eradicate polio? Why things are shaking up quite literally in the USA, and the killer whale using its blowhole to talk human. I'm Georgia Mills.
I'm Chris Smith, and this is The Naked Scientist.
The Naked Scientist podcast is powered by ukfast.co.uk.
For a long time, the World Health Organization have been trying to eradicate polio, and in the last decade they've got within a whisker of making it happen. But the infection is still stubbornly lurking in just 3 countries. So why is this endgame playing out for so long? The countries in question have had recurring conflicts and wars, which people have suggested could hamper vaccination efforts and allow the disease to bounce back. But there was no evidence to support this claim. Now there is. Amal Verma.
Polio is a virus transmitted between humans, and it causes paralysis. There was a time in the world where there were 350,000 cases of paralysis related to poliovirus infection every year. Effective polio vaccine was developed in the middle of the 1900s and actually was released to incredible fanfare with press releases and media attention. It was a huge celebrated event for humanity that they had a vaccine.
And this should be, in theory, an eradicable disease, shouldn't it? It should be possible to wipe polio out.
Yeah, well, in theory, we should be able to deliver this effective vaccine to enough people that would interrupt the transmission of the virus between one human to another, and then the virus has nowhere else to go, has nowhere else to live, and in theory could be wiped off the face of the earth. Overall, the effort's been remarkably successful. So 99.9% of the world's polio cases no longer occur. We're now running into the last stretch, the last mile of the eradication effort. There are only 3 countries that have not yet eradicated polio: Nigeria, Pakistan, and Afghanistan.
And what's stopping us getting this thing over the line?
There are many challenges, logistical and otherwise, to actually eradicating polio from these regions. But one of the barriers that has often been cited is the effect of insecurity or conflict.
Why should that make a difference to the process in these places?
It may make it more difficult to deliver vaccine supplies. It may make it difficult to establish trusting relationships and partnerships with communities. It may induce mass migration. So when you have moving populations, that could make it harder to vaccinate people. The theory that our study investigated is whether insecurity makes it more difficult for vaccinators to access the children who need to be vaccinated. And indeed, we found that that was the most important problem.
So how did you do this? Where did you do it? And what did you actually do to find that out?
We examined polio vaccination efforts and polio cases in northwest Pakistan. That's the region of Pakistan that borders Afghanistan and has been troubled by conflict and is one of the most important remaining reservoirs of polio in the world. We linked publicly available data about conflict-related security incidents with data about vaccination coverage and vaccination rates, as well as data about the number of polio cases in that region.
So you're looking for an association. If there is some kind of instability or some kind of conflict in this area, is that reflected in a change in vaccination uptake? And then the knock-on effect, is there an uptick in the number of polio cases off the back of that?
Yeah, exactly right. We found a 73% increase in the number of polio cases, and we also found about a 5% reduction in vaccination rates when there was high insecurity.
So given what you have found, and this does chime very much with what people had been saying, is probably what's going on. For a long time, they just couldn't prove it. Now that you can actually hold up this data as objective evidence that this is what's going on, what actually can we do about it?
This does highlight three strategies that could be used. The first is efforts need to be agile and nimble to respond to unpredictable changes in access to vulnerable populations. The second is efforts tend to be more effective if you develop trusting relationships with local communities. And so working in that regard to engage local workers can be effective. And that's something that the polio eradication initiative in Pakistan has made heroic efforts, really remarkable work in that regard. And the third is to design strategies that can take advantage of narrow windows of opportunity. So design programs that if you get in, have a narrow opportunity to deliver vaccinations, you deliver a vaccine that's effective in one dose rather than 3 doses. And that's the kind of thing that has been introduced in Pakistan with a new injectable vaccine rather than an oral vaccine.
Amal Verma, he's at the University of Toronto, and that work was just published in the journal PNAS.
And let's hope they succeed in wiping out polio. We're so close. Now, the Human Genome Project, which was completed in 2003, was an international collaboration to read the entire genetic code or sequence of the human genome. That's the DNA recipe that makes you, you. It ultimately took 13 years, it cost billions of pounds, and it involved warehouse-scale buildings full of car-sized sequencing machines to do it. Since those days, though, sequencing technology has come on leaps and bounds. And this week, scientists announced that they've achieved the same feat, sequencing a whole human genome, but this time with a machine smaller than a chocolate bar. And it took weeks rather than years and cost only about £1,000. Lewis Thompson has been hearing how.
Inside each of your cells, a huge amount of DNA is tightly wrapped up. In fact, if all of the DNA from just one cell was stretched out, it would be about 2 meters long, even though it fits inside a space just 1/100 of a millimeter across. This DNA, in its entirety, is called your genome, and it's made up of lots of smaller subunits called bases, A's, T's, C's, and G's. The human genome is 3 billion bases long, and the sequence of these bases is what determines the function of each gene, a bit like a computer code. Being able to sequence a genome quickly and at low cost could affect how disease is diagnosed and treated, and this possibility is now one step closer. Matt Luce from the University of Nottingham told me more.
The goal of this project was to really try and push the boundaries of DNA sequencing on a new technology, which is the Oxford Nanopore MinION sequencer. And this sequencer was introduced about 4 years ago now, and it became clear around a year ago that it would be possible to sequence a human genome on a MinION sequencer. And the thing that's remarkable about that is that the sequencer itself is about the size of a chocolate bar or a small mobile phone. It's an extremely portable device. You just plug it into a laptop and you can sequence DNA anywhere that you want to.
Most genome sequencers used today by scientists are extremely large, expensive machines which require specialist training. The MinION sequencer is much smaller and cheaper. But how does it work?
Essentially, it's a rectangular metal box. It has a cartridge that slips inside it, and that cartridge, or flow cell as we call it, contains a membrane, and in that membrane are lots of nanopores. And nanopores are essentially small holes. And the way that the sequencer works is it applies a voltage across the surface of the membrane. That allows a current to flow through those small holes. And also DNA can pass through those holes. And as the DNA passes through the hole, it of course blocks and changes and alters the current flow. And it turns out that the changes in current flow are proportional to the sequence that's present in the nanopore at that moment in time. So effectively what you get is a current trace, or we call it a squiggle, which reflects the underlying A's, T's, G's and C's.
For several years, the MinION sequencer was much less accurate than the large sequencing machines used by most scientists. However, the technology has now improved to the point of being almost as accurate. And in addition to its size and cost, it has other benefits. Many current methods involve cutting the DNA sample up into tiny fragments of just a few hundred bases to be sequenced. A computer then has to assemble these short sequences together to make the full genome sequence. This takes a great deal of time and can also lead to inaccuracies. The MinION sequencer has a much higher read length. In other words, it can sequence much longer fragments of DNA, fragments which are hundreds of thousands of bases long.
So the advantage of this technology over other competing technologies essentially is the read length that you can generate, plus the real-time nature that you can look at the sequence. So with respect to the read length, we can see parts of the genome that we haven't been able to see before. Things like telomeres, the ends of chromosomes, which can be absolutely critical in understanding particular tumor types. I think the other issue is in nanopore sequencing, in principle, you can start looking at the sequences the moment they appear from the sequencer. And so if you were looking for a particular bacteria or detecting a virus, you can see that the moment that it appears in the sequencer. There are lots of examples of people taking nanopore sequencers into the field. Some of my co-authors were involved in sequencing Ebola during the outbreak, and they went on to sequence Zika virus during the recent outbreak in Brazil, and others are applying this technology in similar situations around the world to get real-time, rapid information about the pathogens in the environment and about their sequences.
So maybe in the future, doctors could use this handheld sequencing technology to diagnose illnesses, whether that's identifying the genome of a particular virus or bacterium, or even sequencing a cancer tumour to work out which treatment would be the most effective. 30 years ago, this would have been impossible. Now, it's looking more and more likely.
It just goes to show size does matter. Lewis Thompson there was speaking with Nottingham University's Matt Luce, and the study that they were discussing just came out in Nature Biotechnology.
Still to come on The Naked Scientist, the killer whales that can talk, sort of, and we meet the people trying to solve the plastic problem. But first, it's time for this.
What happens when the science and technology of space comes down to Earth? Welcome to Down to Earth from The Naked Scientists, the mini-series that explores the spin-offs from space technology that are being used on Earth. I'm Dr. Stuart Higgins. This episode, how a space plasma drill being developed for Mars has already led to a more portable and efficient electric vehicle charger for use in the home. Is there life on Mars? If there is, it may well be hiding below the surface, and scientists from the European Space Agency ESA want to dig into the red planet on future missions to see what they can find. However, drilling deep underground is hard enough on Earth, let alone on another planet. ESA has funded a Norwegian company to study a new drilling technique called plasma channel drilling, which they hope will allow more efficient and deeper drilling on Mars. Plasma channel drilling was first developed by researchers at the University of Strathclyde in Glasgow. It works by placing two metal plates on the surface of a piece of rock and applying a very short but very high power pulse of electricity between them. The voltage between the metal plates can reach up to 50,000 volts, with a peak power of 100 megawatts. That's the equivalent of 1,000,000 100-watt light bulbs, albeit for less than 50 thousandths of a second. The drill head is surrounded by water, and as the voltage quickly ramps up, something unusual happens. Rather than the electrical current taking a shortcut through the water, it turns out that under these extreme conditions, the rock provides less electrical resistance. A plasma channel is formed in the rock. The electrical current can pass through this plasma, heating and expanding it rapidly to cause the rock to break apart. After the researchers licensed out this technology, it was eventually picked up by a Norwegian company who are now aiming to turn it into a viable space plasma drill for future missions. And key to the effectiveness of the plasma drill is its power supply, which needs to rapidly produce pulses of high voltage. Room and available power are always limited on board spacecraft, so this forced the company to develop a new form of electrical transformer. A transformer is essentially two coils of wire wrapped around a common metal core, and it's used to turn low voltages into high ones and vice versa. The Norwegian company developed a new transformer design that both generates high voltages and is also extremely compact. And in doing so, they realised that the same technology could be used to improve the way electric vehicles are charged at home. The company could reduce the size of a home car charger, which is effectively a giant phone charger for your car, from around 100 kilograms to about 2 kilograms using the transformers it developed for space plasma drilling. And unusually, while the technology hasn't yet been used in space, the spin-off from it is already available to consumers back here on Earth. So that's how developing a space plasma drill for Mars helped lead to portable home chargers for electric vehicles. That was Down to Earth from The Naked Scientists. My name is Dr. Stuart Higgins, and you can find more episodes online at nakedscientist.com/downtoearth.
And Stuart will be back in a couple of weeks to bring something else down to earth.
We're back down here on the ground with a bump, and I mean a really big bump. In recent years, the state of Oklahoma in America has been subject to hundreds of earthquakes. A decade or so ago, though, it was recording only one or two. Why the difference? The answer, a new study suggests, is it's all down to the oil and gas industry. Contaminated water that's been used to force out oil under pressure from below ground is being disposed of by injecting it back down into the deep bedrock, where it then causes things to slip and slide about. Izzy Clark.
Oklahoma, a state that's home to 4 million people, where the voicemail was invented, and in the 20th century produced the most oil of any state or territory in the United States. In fact, oil was first discovered there by accident in 1859, but now they've got another accident on their hands that's shaking things up.
My name is Tom Gernon, and I'm an associate professor in earth sciences at the University of Southampton. Oklahoma has experienced some pretty intense seismicity over the last decade. Seismicity is the frequency at which earthquakes repeat through time. And in the case of Oklahoma, if you think back to 2008, they had one earthquake which was over magnitude 3. By definition, an earthquake that you can feel. In 2015, the number of earthquakes was 903. So that just gives you some sense of the scale of the problem here. So these earthquakes are linked to the injection of water underground into deep rock formations.
The reason for this process is to extract oil from the ground. Across Oklahoma, there are 10,000 or so wells where water is injected at high pressure deep underground to help release oil and gas, which is locked up in the rocks. This contaminated water and oil combination then comes back out of the well, is separated, and yes, the oil companies have their oil, but what about all that wastewater?
If you think about it, you've got 2.3 billion barrels of wastewater, and you're in a sort of landlocked state in the center of the US. It's very expensive to ship it elsewhere to be processed and maybe treated and disposed of. So it's economically more efficient to inject this deep underground because it's otherwise very expensive to get rid of.
This constant cycle of injecting wastewater into the ground not only weakens the rocks but acts as a lubricant, which is part of the problem. The University of Bristol and Southampton University developed a statistical model that was able to analyse a combination of impacting factors.
So what we looked at was data from these injection wells, the injection volumes, injection depths, and injection locations through time. So we looked at all these different parameters and the correlations between those different parameters and the seismicity, the earthquakes that are happening within a given radius of the injection wells. And I should say, typically the injection depth is about 1 or 2 kilometres beneath the surface.
Now, the injection depth a few kilometres underground was a huge factor for the frequencies of these earthquakes due to the type of rock lying there.
The wastewater is normally injected into sedimentary rocks, which are overlying much deeper crystalline, very old rocks. You can think of granites maybe, or metamorphic rocks, which are heavily fractured and so on. Liquids can then find their way downwards, basically, into the boundary between these two different rock types. And we know that most of the earthquakes in Oklahoma are actually happening in these deep, what's called crystalline basement rocks. These are presumably very heavily fractured. There's lots of old ancient faults in there which allow sort of stress to build up and release. So we have most of the big earthquakes which have happened over the past decade have actually been in this rock. So the closer you inject to that level, the more earthquakes you're going to experience. And this is incredibly important. It's not been shown before. It carries a lot of implications for regulation in Oklahoma and potentially elsewhere. The operators could use this information to change their practices and potentially raise well levels to reduce the earthquakes that are happening.
Another key finding was that there's even a time lag. Wastewater would be injected into the ground and the resulting earthquake would then hit a few months or even years afterwards. With over 2 billion barrels of wastewater injected into the ground every year, for Oklahoma, worse may be yet to come.
Another thing we need to consider is that the oil demand hasn't really been very high over the last 2 years. The number of earthquakes has dropped slightly since 2015, Although we have had some of the biggest earthquakes, and the magnitude 5.8 Pawnee earthquake, which struck in September 2016. This is the largest magnitude earthquake that has ever happened in Oklahoma, and this caused injury and damage to buildings. So this happened at a time when the injection had actually been reduced by the regulators. This shows that there are these potentially significant time lags between injection and seismicity.
So it's not just the carbon cost of the oil industry that we need to worry about. That was Southampton University's Tom Gernon, and his study just came out in the journal Science. Now finally, can you speak whale? It's time to take a look at one other story which has been making big waves this week, and Georgia Mills has this report.
Hello? Hello? Hello?
This is Wiki. She's the first killer whale ever to be recorded imitating human speech.
1, 2. 1, 2.
The point here is that we didn't want to teach English or a language to the killer whale.
That's study author Jose Zamorano Abramson from the Complutense University of Madrid. So why did they do it?
Vocal imitation is a hallmark of human spoken language. It's very important in the evolution of human culture. The weird thing is that studies in other species has revealed that the ability to copy sounds from other members of their own species among primates is mostly unique in humans.
Our ability to mimic is an important part of the development of our language, but it's largely absent in our closest cousins. Apes, despite their name, can't. It is seen in a few other species, famously parrots, and in marine mammals. Killer whales are particularly interesting because scientists have seen that different groups, or pods of whales, have different dialects, just like accents.
And most biologists think that these dialects are acquired non-genetically and probably by social learning.
To test whether this really was the case, Jose and his team saw if 14-year-old orca Wiki could successfully imitate new sounds, either made by another killer whale, her calf Moana, or by a human.
1, 2, 3. Amy. Amy.
First, we found that killer whales made recognizable copies of novel sounds of killer whales and even human sounds or words. They did it quickly. So, we found they are flexible, open vocal learners. They have the capacity for vocal learning and for imitation, vocal imitation. Our results are also remarkable if you think that there was no extensive trial and error training. The sounds were presented in the air and not in the water, so it was a very artificial medium for her. Also, the sound production system is greatly differs from humans. They use another vocal structure than humans, and so it's remarkable that she was capable of copying our human sounds.
Audio analysis software was used to make sure the imitations really did match up with the target sounds, although some of them were better than others.
1, 2, 3.
We support with these results the hypothesis that dialects observed in natural populations are learned by imitation, which means that these dialects can be seen as vocal traditions or cultures. If they have, like vocal traditions or cultures, and dialects are important part of these traditions, dialects can also serve like a social function, like accents, for example. Killer whales can differentiate where are the members of their group or from other families just by the accents, by the dialects, and they can enhance cooperation, for example.
And what does this mean for our own treatment of these marine mammals? Jose points out if they do learn socially from one another, taking a member out of a pod can be more damaging than we thought.
You know that if you capture, for example, a killer whale or other animals that relies on social learning, and some animals are very important for their social knowledge, you can have a lot of damage if you took or you kill the animals that have the knowledge, because different animals play different roles in the social structure. And the same reason happens with the killer whales that are in captivity. You cannot release a killer whale that is captive in the ocean because she relies in social learning. So you really need to teach that killer whale the special cultural dialects or the way they hunt or whatever to introduce them, if it can be introduced.
Incredible what they can do, isn't it? That was Jose Abramson, and that study came out this week in Proceedings of the Royal Society B.
And if you'd like to follow up on any of the stories which we've been discussing so far in the programme, you can find the references and complete transcripts as well as all the audio on our website. That's nakedscientists.com. Follow the links to podcasts.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
If you want to drop us a line about this programme or any other, the email address to use is chris@thenakedscientist.com, and you can find us on Twitter. It's @nakedscientists. But now it's time for the main theme of this programme, and that's plastic. It's inescapable. It's in places you'd expect, like in packaging, but also in our clothes, many of our cosmetics, and even our tennis balls. There are plastic bags lying at the bottom of the ocean, and we've even gone and left a load in space. So when did we turn into a world of plastic?
By combining the phenol with the formaldehyde, we produce the phenolic plastic.
The first man-made plastic, which is Parkasine, was created in Birmingham in the 1850s. Since then, scientists have unlocked the alchemy of even more polyethylenes, propylenes and styrenes, and it's taken the world by storm.
But today is the era of plastics.
You'll love our new, easy-to-handle 2-liter plastic bottle.
It's the crystal clear plastic that lets you see everything you wrap.
Cling film, bottles, bags, even your lawn.
The latest thing in garden technology may be the answer to your problem. It's this stuff. Plastic grass. The tufts are made of polypropylene and they're woven onto a base made of the same substance.
It's everywhere, and for good reason. It's cheaper than glass to make, it's less likely to shatter, it can block out bacteria, keeping food fresh, which avoids food waste, and it's lighter than other storage materials, which reduces transport costs and, of course, the carbon emissions. But the cons that come with these pros are building up, alongside the mountains of plastic. We know it doesn't degrade. We know it's filling up our oceans, killing turtles, whales and albatrosses alike. We know it gets ripped down into tiny pieces that enter our food. But still, we're producing about 300 million tonnes every year. But could things be about to turn around?
Plastic-free aisles in supermarkets are among the ideas being put forward by Theresa May.
And the plastic problem, the UK under pressure to find new ways to recycle. Now,
Theresa May pledges to eradicate all avoidable plastic waste by 2042.
Because two things have happened recently which might spell a change.
Since its invention some 100 years ago, plastic has become an integral part of our daily lives. But every year, some 8 million tonnes of it ends up in the ocean. And there, it can be lethal.
Blue Planet 2 aired, highlighting the dramatic impact on our oceans and the animals that live there. And
China no longer wants to be the world's rubbish dump. It's going to ban the import of 24 kinds of waste.
China, who have been accepting a lot of plastic waste from the West, have said no more. So people and governments all over the world are looking for plastic-free solutions. But can we give up our love affair with plastic? And can science help? Indeed. Well, that's what we've made it our mission to find out this week. Can science solve the plastic crisis? Later, we'll hear about the company who thinks they can use waste plastic to build better roads, and the scientists making plastics from poo. But before that, let's get up close with the chemistry of the stuff. Cambridge University chemist Stephen Lee joins us. Hi, Stephen.
Hello.
Let's start with the basics then. What is a plastic?
So a plastic, when chemists think of plastics, what we're thinking about is a repeat monomer unit. So the word polymer, you may have heard, that's how chemists generally think about plastics. And that's essentially a big long chain molecule that consists of much smaller molecules that link together, typically via a carbon-carbon link.
So a monomer is like a little unit, a little pod, and then a polymer is a load of these strung together.
Exactly. So poly meaning many and mer meaning unit comes from the Greek polymer.
It all makes sense. So how do you make a plastic?
There's lots of ways to make a plastic, and they have very large meanings. But I think in the general terms, when people think about plastic spade or some wrapper, the way you do that is you take typically a small molecule that has a carbon-carbon double bond in, and you apply it by various different heats or chemical reactions. You can encourage that to form long chains, and that typically can be done via small molecules that come from the petrochemical industry, for instance.
And so why does it stick around for so long?
Well, the reason is there's not the traditional methods for things to degrade. So when we think about things rusting or trees or organic waste being digested, there are kind of biological organisms that have very specific, that have spent billions of years evolving lots of complex pathways to be able to break those bonds. So in the case of, say, cellulose, that's a polysaccharide. So that's a polymer as well, but it's made of lots of sugar molecules. But in the case of a polymer like the plastic bag at a shopping centre, that's typically made of polythene or polyethylene. And so that's a very different kind of chemistry. One's got to break a carbon-carbon bond. And that's much harder for the natural world to break down. And so unfortunately, we just haven't had the bacteria and other environment haven't had time to kind of deal with that.
Right, so something like cellulose, which is actually kind of similar to a plastic, can be broken down just because it's been around for millions of years within plants.
That's true. It's called a biopolymer. So there's three kinds of kind of biopolymers, but what we're talking about here is this unusual class, which we see every day, but on the time scale of evolution is a relative newcomer. We've only had the first completely synthetic plastic since 1907.
And why can't we just recycle it? Why can't we put it like in the opposite way through the plastic machine?
Yeah, that's actually a thermodynamic answer to that. So it's to do, all the technology to understand why plastics don't mix is the same chemistry and the same physics that we worked out in the Industrial Revolution. And in fact, what it's to do with is that if you take two compounds and try and mix them together, sometimes they mix, sometimes they don't. Polymers don't like to do that because they don't gain as much entropy. It's a term about how disordered something is. So what that really means is because polymers don't mix, if I just take a mixture of my compounds and try and just heat them up to kind of regenerate a big slush of plastic, it means that they all phase separate. So they form much like oil and water don't mix. You get the same thing with plastics. And so what that really means is it's actually quite difficult to separate them out in order to recycle them in a way that, for instance, aluminium or metal isn't quite as difficult.
And I guess quite often within the same product, you have a few different types of plastic.
Absolutely,
all in one place.
Yeah, so
anyway.
if you look very carefully on the bottom of your plastic bag or on the bottom of your bottle of Diet Coke, you'll see that there's a little mark, and that determines the type of plastic. And what that means is that if you have polyethylene or polythene, that's possibly recyclable with other clumps of polythene, but it's not if you use polymethyl methacrylate or polystyrene or any other synthetic polymer we use traditionally today.
Could we use nature to help us then? Is there anything out there that might be able to munch away at these carbon bonds?
There's precedent in the literature for various bacteria and also fungus to degrade very specific types of plastic. Now, in biology, there's lots of ways in which we can digest plastic, but the chemistry to be able to digest these specific compounds is just unusual and therefore doesn't exist a lot. Unfortunately, there absolutely could be, but we haven't really found anything yet. There have been some studies where people actually, the way they look for them is they look in and around plastic plants, because they think if bacteria could start eating plastic, it would be a limitless source of food. It's an all-you-can-eat buffet of energy to a bacterium. So there is a clear kind of push for them to be able to use it. Unfortunately, normally what happens is we have to find ones that have because all of the chemistry I was talking about is very specific, it means that bacteria have to evolve different ways to be able to digest specific plastics. So you don't get one bacteria that will eat all plastics, but there are examples of bacteria that eat very specific kinds, but not very well at the moment.
Right, and very briefly, do you think we could modify something in a lab, a super bacteria, to just go into the oceans and destroy all the plastic and solve all of our problems?
Yeah, catch a spider to kill a fly. So it's possible, and I think loads of people are working on really interesting ways to be able to modify bacteria. We have lots and lots of genetic tools in the laboratory to be able to change bacteria to do our bidding, as it were. The trouble is that the specificity to be able to break this carbon-carbon bond in my plastic bag and not break the carbon bond in me is very different, and that's the challenge going forward.
I suppose we wouldn't want that. So thanks very much, Stephen Lee from the University of Cambridge.
Thanks.
That would be awful, wouldn't it? End up with bacteria that like to break down yourself. So it doesn't look like degrading plastic naturally is currently an option that's on the table. And what, therefore, can we do with the piles of plastic that already exist in nature? Perhaps we could use it to solve another problem that we have. And that's what Toby McCartney is aiming to do with his company, Macriba. So, Toby, what's your solution?
We take waste plastics, and I think it's important to say waste plastics. So these aren't recyclable plastics. These are plastics that are destined for landfill. We take those and we mix them in with an asphalt mix, so a road mix, to replace part of the bitumen, which is another form of carbons, to make a longer lasting, sometimes stronger, sometimes more elastic road structure that doesn't pothole as readily.
Can you use any kind of plastic for this? So it wouldn't matter if you had a mixture?
Because of what Stephen was saying there, we can't just take any old plastic and shove it in. It has to, we call it homogenize. It has to mix in well with the remaining of the bitumen that's in the mix so that it works together to do different things to various different roads. We basically make cakes of various different waste plastics.
Talk me through the process then. So you take some plastic, how much do you need? What do you do with it to make it road ready? And then how is it deployed into the field, or road even?
Yeah, well, we take those plastics. Some of it comes from commercial plastic, waste plastic. Some of it comes from our councils, so household waste. And most people see a plastic bottle, say, as just a plastic bottle. But actually, there's 4 different types of polymers, 4 different plastics within one bottle. You have the bottle that's made from a particular type of plastic, and then the lid that goes on, that's another type of plastic, and then the wrap, that's another type of plastic. So what we do is we separate them all out, and then, as I say, like a cake mix, really, in fact, we have 3 different cake mixes where we put those polymers back together so that they work in to replace part of the bitumen. That's the oil base, the black stuff that you'll see in a road. Those pellets that we produce, the cake that we produce, that's added in at the same time that the asphalt is manufactured. So the bitumen's taken out and our pellets, our plastic pellets, are then added in. We replace anywhere between 5 to 20% of the bitumen content that goes into a road. A road's mainly made up of stone, so aggregates. Maybe 90% is aggregates, and then the sand and stuff that goes in there. But up to 10% of the content of a road is the bitumen itself.
How does it perform in practice?
It's absolutely fantastic. We've had trials down now all over the UK. We're just about to launch in places like Australia. Over in Bahrain, we've got roads down, and the GCC countries. For testing, we have to meet a British and European standard, and we overly meet that. So it performs much better than a standard asphalt.
In what way? In terms of wearability, durability?
We have 3 different products, if you like, or 3 different cakes. One of them gives a higher tensile strength, so it makes the road basically stronger. So if you've got heavy goods vehicles, lots of traffic on a road, it's very good to create a stronger road. Another product adds some flexibility into the road. So up in, say, Scotland or over in Canada, where we have lots of freezing conditions, what happens is, as we get a lot of rain, the rain gets kind of soaked up into the asphalt and is stored in tiny little air pockets within the asphalt. As that water freezes, and we know the science behind this, that water then expands, and often we'll see on our roads lots of cracks and therefore potholes. Well, one of our products gives an elastic quality, if you like, to the asphalt, so it reduces those cracks and therefore reduces those potholes.
What about the environmental impact? Because one of the reasons people are so concerned about plastics is that wear particles, ground up plastic, ends up in the ocean. It then becomes fodder for filter feeders, and it can concentrate other pollutants and things up the food chain, as well as being directly toxic for marine animals. And it's not good on land either. Is there not a danger that if you put lots of plastic on the roads, that it's going to wear down as vehicles go over the road surface, and therefore it'll turn into plastic particles that wash into drains and end up in the sea anyway? We're back to square one.
Yeah, I think there's 2 points here. The first is you have to remember where our plastics are coming from. So they are from landfill or destined for landfill. And what happens when that goes to landfill, a lot of it's blown out into our rivers and then off into our oceans as whole plastics. Now, we're taking those plastics, and we can only take the ones that become part of the bitumen that's in the road. So there's no microbeads. You may have heard of microbeads. There's no plastics present in the road. It becomes part of the bitumen. The bitumen is the binder, so that's the sticky stuff that sticks a stone together. That's a little bit like at the moment we have Pritt Stick in our roads, and what we produce with our asphalt manufacturers is the superglue. So if anything, it stops the leaching of that bitumen going off into our rivers.
Let's hope it does. Toby, thank you. Toby McCartney from Macreba. We wish you luck with your trials, and hopefully you'll come back and tell us how you got on in due course.
Hello, Katie here, to let you know that the Naked Scientists are hiring. We're looking for a talented radio producer to join our team here in Cambridge. If you love communicating science and have a passion for podcasting, then we'd love to hear from you. Head over to nakedscientist.com/job for more information about the role and details on how to apply. And the deadline is fast approaching, so don't leave it too late. Now, back to the programme.
This is The Naked Scientist with Chris Smith and with me, Georgia Mills. And this week we're looking into how science can solve our plastic problem. Plus, in the cold weather, what keeps you warmest, walking or running?
One of the problems with plastic is that it just won't break down. So could we switch to an alternative that isn't so long-lasting? Bioplastics aim to do this by using alternatives to oil in the production process, and one team is aiming to cut waste even further by making bioplastics from waste itself. Georgia Mills spoke to Damien Laird at Murdoch University in Perth, Western Australia.
We like to tell people that we're making plastics from poo, but in reality what we're trying to do is utilise resources that are in waste streams and turn them into something profitable, rather than basically just treat them and send them out into a stream, try and make a product out of them.
What kind of product can you make from sewage?
So to be frank, we don't quite use the sewage. We use the bacterial cultures that are in the sewage, and they can actually produce a bioplastic. And that's biodegradable, and we can use it for packaging and lots of other types of things and replace oil-based plastics.
Would this look like an ordinary plastic? Would it smell?
Yeah. No, they just look like ordinary plastics. At this stage, they definitely don't smell. The cultures themselves don't even smell, which is great because it makes the lab much more interesting. But yeah, basically we're hoping that we can reproduce the same characteristics of an oil-based plastic, but hopefully use a biological process to get it done. So whilst the biological process is cleaning the water, we're getting a product at the same time.
How does this technology work?
My name's Leonie Hughes and I'm a lecturer at chemistry at Murdoch University in Perth, Western Australia. Basically, it's the equivalent of us eating too much food and getting fat. So the bacteria are put under conditions where they are given far too much food but not enough of an oxidant source, such as oxygen or ammonia or something like that. So they get too much of chips and not enough fruit and veggies and exercise. And under those conditions, they effectively store the rich carbon source that they get given so that they can hide it from other bacteria. It's an evolutionary thing that advantages them over other bacteria. And then under conditions where they suddenly have no external source of carbon, but a rich source of oxygen or ammonia, that they can then use that to continue growing when no one else can.
I'm imagining bacteria equivalent of a hamster stuffing seeds in its cheeks.
Pretty much, and it actually forms vacuoles in the cells that you can visualise as big lumps of plastic, basically.
What do you have to put into the bacteria to get this plastic out?
Many bacteria are shown to do this. Obviously, some are better than others. You basically just need to give them something like glucose or vinegar, something rich in carbon, and let them do it. Just try not to give them too much oxygen or too much nitrogen at the same time, and they pretty much go for it themselves.
And then they create these bags of plastic in their cells. How do you then get this out of them?
Well, at the moment, this is the unenvironmentally friendly bit, potentially. This is the bit where we have to use solvents and things to actually kill the bacteria and extract out the plastic. So that part of it at the moment is not looking particularly nice. However, there are some people doing some research in similar areas with things like algae that can extrude things like bio-oils or potentially even the plastic. So there are other ways of looking at it.
How is this plastic different from ordinary plastic?
It's not. It's what's classed as a thermoplastic. It still has the same kind of properties that plastics that you see in shampoo bottles and things have. It does need some post-processing, so it doesn't have the cross-linking and things, the more complicated third-degree structure that plastics have that get used commercially. But those are things that you can add in a chemical sense after they've been extracted from the bacteria. We might be able to design the feed that we give the bacteria better to actually enhance the production of copolymers, so polymers made up of more than one monomer, more than one building block. And if we do that, the plastics will come out closer to commercial plastics at that point already.
How easy will this be to scale up? How are you going to get a usable amount of plastic from this process?
Yeah, it's not trivial. So we would have to do things like high density cell cultures, and they're quite hard to manage. So you would need to have membrane technologies and things like that to have maximum number of bacteria in small footprints of space, so that you've got minimal amount of water, maximum amount of bacteria, and therefore ease of extraction of the bacteria. So these are not trivial questions. But if we can get the technology working at the lab scale, then that's kind of where we would link up with an engineer who would solve, hopefully, those problems for us.
And then at the end of this process, you hopefully have a plastic that is biodegradable. Why is it biodegradable?
Just sheerly because of the nature of why the bacteria make it. They make it so they have a carbon source later when they have abundance of oxygen, but they don't have any carbon external to the cell. It has to be degradable by them, otherwise they wouldn't have made it for the advantage of getting the fat in their cells and stealing it from other bacteria. So that automatically means it's biodegradable.
Best case scenario, what are you hoping that this can do?
So the big picture is that we could basically, hopefully, locate one of these plants next to an industrial site, take their wastewater, clean up the nitrogen in particular that comes out of it that the bacteria can use, and then also produce basically a product. And we can hopefully create a product that we can change that product at will and for different uses. One of the really big ideas we'd like is not just to take traditional waste streams like they come from, like you would expect in a wastewater treatment plant, but industrial waste streams as well. So there are lots of industries, wineries, for example, breweries that use bacterial cultures to clean their water before they release it, but that contains a lot of carbon. And we hope that what we can do is actually create these polymers from that waste carbon in a sense, and then actually be able to produce, maybe the packaging for the beer along the way, in a sense.
Using a product that would have been created anyway by this other process and otherwise gone to waste.
Yeah. And so that whole process then becomes very microbiological because you use yeast to make the beer in the first place, bacteria and yeast to clean the water and then produce the packaging potentially for the product, which is amazing.
I could drink to that. That was Damien Laird, and before him, Leonie Hughes from Murdoch University in Western Australia. So, Stephen, why aren't bioplastics bigger? They sound like a great solution to the whole problem.
They're a great solution. Unfortunately, the feedstock from where we get that monomer unit, that fundamental unit from which we build these polymers, has to come from somewhere. And so traditionally, we use that comes from the petrochemical industry, so things like ethylene and other compounds that have this double bonding. One can use bioplastics perfectly well. A good example would be polylactic acid. If anyone's ever had a dissolvable stitch, if you've ever cut yourself and gone to A&E, that's an example of a bioplastic, which is just dissolves over the period of months. But the feedstock for that is made from sugar. So that's just more expensive than it is just to use the offshoots from the petrochemical industry.
Don't they use starch in some plastic bags these days, Stephen, to make them fall apart more?
It's interesting. The plastics industry spent the first 50 years trying to make their plastics last longer and have better mechanical properties, and they've been spending the last 20 years trying to make them fall apart faster.
And so I guess throughout the show we found a lot of things people are working on, but there doesn't seem to be any kind of silver bullet on the horizon here. So I suppose what I've learned is that I just need to reduce the amount of plastic I use. And Chris, you and me should both hang our heads in shame because we both bought in plastic-wrapped food.
We were discussing this before the programme because Stephen, we offered him some cake. He didn't want any, but I brought in cake of the week covered in cling film. Georgia turned up with brownies. Both foodstuffs are delicious, but unfortunately they are covered with environmentally extremely unfriendly and not on programme message coatings and packaging. Not good. It's a classic case of do what I say, not what I do.
Stephen, I'm curious, do you have any top tips on reducing our own plastic consumption?
It's not what one would consider traditional, but one way you could reduce your plastic use actually is to kind of think about trying to use alternative forms of transport, things like electric cars. So the majority, when we take crude oil out of the ground, the majority of that oil is used to make petrol. But all of the stuff that's left over is the feedstock for our plastic. So if we can reduce our need and our demand for the petrochemical industry, we're decreasing our need to be able to use this byproduct to turn it into plastic.
That's a really interesting point. I hadn't really thought of that, the fact that plastic is being used from a byproduct, so why not turn it into something?
Absolutely.
The other point, because someone said to me the other day, Stephen, I don't know what your take is on this, that we should just package all these things we see in the supermarkets in paper, for example. But then I pointed out, and maybe you can tell me if I'm right, that, well, actually, you've got to factor in that if I package the food stuff in plastic, it lasts longer. It has a longer shelf life. Therefore, we're probably going to throw away less food. And we know that rearing meat is incredibly bad for the environment in terms of carbon emissions, transportation of the meat, disposal safely of waste food, and so on. So that it's not just as simple as what we use to package stuff up, is it?
Absolutely. So what you really want to think about is the total energy content. And so that includes everything, as you say. Quite often people might use their carbon footprint. It's a similar kind of quantity. It's how much energy is required to make not just your apple, but your apple packaging and put it in a truck and move it from the other side of the world. That's the thing you want to minimize. And so there's obviously a lot of interest into being able to use local food, because actually what you're doing there is reducing your energy footprint. And that's ultimately the goal of these things, is to reduce the amount of energy required to produce these packaging materials.
Can we just bring in Toby at this point? Toby from McCreeba, is this sort of analysis the kind of thing that you did when you were considering the impact and doing the impact assessment for your road surfacing project?
Yeah, I mean, we look at our business from a carbon emission standpoint. Unfortunately, the construction industry is pretty bad for releasing carbon emissions in everything that it does.
40% of the world's CO2 is from concrete, isn't it?
Yeah, that's right. Yeah, so we're looking to reduce those by using less bitumen. We've worked out that we save a ton of carbon emissions for every ton of bitumen that we replace, which is quite hefty, really.
Stephen, do you have any points on Toby's business?
Yeah, I mean, I think the interesting point here is that I don't think anyone is trying to reduce plastic use completely. And I think that's an important point. There's always going to be a need to be able to use it. It's a wonder material that we have. And to think that it's all bad under all conditions is wrong. I think what you want to do is think about a way to stimulate the economics of such that if we do really need disposable plastics, that we make biodegradable plastics more economically viable, and in which case all of the problems will go away because people will instantly switch to these more renewable sources.
Toby, would that spell trouble for you if you used up all the plastic in the landfill?
Unfortunately for the rest of the world, if we stop producing plastic today, McCreeba, we would still have enough to lay every new road around the world just with the waste that we produce at the moment. So stopping it isn't going to stop our business. So we would love it to be stopped, but it won't have any impact on our business.
Well, it's incredible the amount we've made. Thank you so much. That's Toby McCartney from McCreeba. And thanks to all our other guests this week. That's Stephen Lee, Damien Laird and Leonie Hughes.
And to finish off this week, it's time for Question of the Week. And Izzy Clark has been chilling out with this question from Trent.
Hey, Naked Scientist. The temperature where I live recently hit minus 40 degrees. And it got me thinking, is it better to walk or to run through the cold air? Should you run to reduce the amount of time out in the cold, or do the adverse effects of moving faster, like wind chill, outweigh the benefits of getting to your destination quickly?
When you go outside and stand in the cold, your body is much warmer than the air around you. Because heat likes to flow from hot to cold, it warms up the air next to your skin, and this creates a kind of warm air blanket that slows down further heat loss. But if it's windy, or you start moving, then the warmer air molecules are pushed away and you'll be exposed to new cold air. So running means you lose more heat to the air, but we all know running warms us up. The faster you go, the more heat you generate, and you get to your warm, cosy house much faster. So what's the best strategy? It turns out whilst you are generating heat when you run, the air takes away that protective layer rather quickly at slow speeds. So if you're not the fastest runner, it's better to walk through the cold than break into a light jog. Now, there are a few factors to work out the minimum running speed where the heat you generate finally balances out the heat you lose due to air movement. For example, the surface area of an adult human, how much heat energy they generate, plus the effect of wind on heat loss. But even so, this calculation applies to heat loss of bare skin. I mean, we may be the naked scientists, but we certainly don't advise running at minus 40 degrees in your birthday suit. All jokes aside, clothing's actually an important factor here. While running slowly through the cold air naked might get rid of your warm air blanket, if you wrap up tight, your clothing will trap the warm air, preventing wind chill on your skin. So, to sum up, either stay put or wear appropriate winter clothing, or run very, very fast. Next time, we're simmering down to this question from Steve.
Switzerland has now banned boiling lobsters alive. Do they experience pain? How do we know?
What are your thoughts? You can email chris@thenakedscientist.com, you can find us on Facebook, you can tweet @NakedScientist, or you can join the debate on the forum, thenakedscientist.com/forum.
And that, I'm afraid, is it for this week. Thank you very much to Georgia Mills, who put the programme together. Do join us next week, where we'll be looking at how science meets art. The Naked Scientist comes to you from Cambridge University. It's supported by the EPSRC, the STFC and Rolls-Royce. I'm Chris Smith. Thank you very much for listening, and until next time, goodbye.